This webcast discusses how to analyze circuits that have series wiring. When we say that a circuit has components wired in series, we mean that those components come one after the other in the circuit. That means that as the current flows through the circuit, it first flows through the first component, and then it exits that component, and then it will flow through the second component and exit that component, and so on. That means that there are no places for the current to split, and so the same amount of current flows through every component in the circuit. So if you have resistors that are wired in series, it is sometimes helpful to talk about the equivalent resistance. In other words, if I had three resistors, R1, R2, R3, could I replace those three resistors with one resistor that has the same total amount of resistance? That is easy to figure out for components that are wired in series. The equivalent resistance simply equals the sum of all of the individual resistors. So here, the equivalent resistance would be the sum of R1 plus R2 plus R3. And once we've determined the equivalent resistance, you could replace the three different resistors with a single resistor that has that equivalent value, and the circuit would work in the same way. Here's an example of a circuit that is wired in series. There's one battery with a 20 volt potential difference across it, and there are two resistors. R1 is 6 ohms, R2 is 4 ohms. The equivalent resistance would be the sum of R1 and R2, and so it would be simply 6 plus 4, which is 10 ohms. Once we know the equivalent resistance of the circuit, and we know the potential difference across the ends of the circuit, because the 20 volts is across the terminals of the battery, then we can find the current that's flowing through this circuit. We use Ohm's law, and we take the delta V across the battery and divide by the equivalent resistance. Once we know the amount of current that's flowing in this circuit, we can then use Ohm's law at individual components, and so we can find the delta V, the potential difference across each one of these resistors. So for resistor 1, which is a 6 ohm resistor, the delta V would be the current going through the resistor multiplied by that resistance. 2 times 6, there would be a 12 volt drop in voltage across resistor 1. For resistor 2, which is a 4 ohm resistor, the delta V would be 8 volts. This gives us a chance to see that this circuit does conform with Kirchhoff's loop rule, which tells us that the sum of the delta V's, which are gains in the circuit, should equal the sum of the delta V's, which are drops. So there's one gain in this circuit. There's a delta V increase, an increase in voltage going from the negative to the positive terminals of the battery, and that's 20 volts. And then there are two voltage drops, the delta V across resistor 1 and the delta V across resistor 2, and those happen to equal. The 20 volts gained across the battery equals the sum of the 12 plus 8 volt drops across the two resistors. Let's go work a few more problems with this. So I'm going to go to worksheet 9D, and where we've got several problems dealing with series wiring. So the first, it says we've got three resistors connected in series, and we want to know the equivalent resistance. Well, the equivalent resistance would equal the sum of these. So it's going to be 15 ohms plus 30 ohms plus the 50 ohms. And so it's going to be a total of 95 ohms. In number 2, it says, oh, there are 250 30 ohm resistors connected in series. So I would need to add 30 ohms 250 times, or I could just multiply, I guess. So the equivalent resistance here would be the 250 of those 30 ohm resistors. Which would be 7,500 ohms. That's the equivalent resistance for that circuit. Items other than resistors can be wired in series, and we've done a lab where we wired batteries in series, and we saw that when you wire batteries in series, the delta V's add. Okay, so here we have a flashlight, and the batteries are stacked in series. It takes 4 of those 1.5 volt batteries. So we've got 4 batteries in series, and then there's the light bulb. Okay, each one of these batteries is 1.5 volts of potential difference. So 1.5 volts of gain across each one of those batteries, and then the bulb has 11 ohms of resistance. Okay, and so they're asking us what is the current. So the total delta V across the batteries is going to be 4 times the 1.5 volts, which is 6 volts. Okay, and then I can find the current moving through this circuit. The current would be the delta V across the battery divided by the equivalent resistance. So I have 6 volts of gain across the batteries, and there are 11 ohms of resistance, and so the current is going to be 0.545 amps. Here we have a portable heater. It's powered by a 45 volt battery, and it has 4 identical heating elements. They're wired in series. So I've got 1, 2, 3, 4 of those resistors wired in series. There is 11 amps of current running through this circuit when the heater is turned on. We'd like to know the resistance of each heating element. Well, I know that the equivalent resistance of this circuit would be 4 times the resistance of each heating element, which is 4R. And so by Ohm's law at the circuit level, the equivalent resistance should equal the delta V across the battery divided by the current. So we have 45 volts, 11 amperes, and so the equivalent resistance is 4.091 ohms. Well, since the equivalent resistance, which we just found is 4.091 ohms, equals 4 times R, R is going to be that 4.091 divided by 4, or 1.023 ohms. That's what each individual heating element has as its resistance. Okay, in number 5 here, the total delta V potential difference across 2 resistors in series is 34 volts. So I've got 2 resistors in series. I'll just call them R1 and R2. And then the total delta V is 34 volts. That's almost like I'm putting a battery across them, and I could say that that battery has 34 volts of delta V. The current is 6.5 amps. Okay, we know that one resistor's resistance is 2 ohms. So this one is 2 ohms. And we'd like to know, what is the resistance of this other one? We don't know that one. Okay. So if I look at this, since I know the total delta V across the circuit and the current, I can find the equivalent resistance using Ohm's law at the circuit level. So the equivalent resistance must be the delta V across the battery divided by the current. So that's 34 volts divided by the 6.5 amps. And so the equivalent resistance is 5.231 ohms. Another way to find equivalent resistance is to add the two resistors that are in series. So that's R1 plus R2. So therefore I know that the equivalent resistance, which is 5.231, equals R1, which is 2 ohms, plus R2. And so I can solve for R2. It must be 3.231 ohms. And then the last part of this worksheet, we have two circuits. They're both wired in series, and we just want to analyze each one. So first we're going to find the equivalent resistance. Let's look at number A first. So the equivalent resistance is the sum of all of the resistors that are wired in series. So here that'd be 10 plus 12 plus 25, which is 47 ohms. And then we can find the current flowing through the circuit. It's going to be the delta V across the battery divided by the equivalent resistance. I'm just using Ohm's law at the circuit level. In this picture, it looks like the delta V is 12 volts. The equivalent resistance is 47 ohms. And so we have a current of 0.255 amperes. So then it wants the voltage drop across each resistor. So here I'm going to use Ohm's law, but at each component level. So the first resistor is 10 ohms. So the voltage drop, delta V, would be the current times the resistor. So 0.255 amperes times the 10 ohms would be 2.55 volts. For a 12 ohm resistor, the delta V, again it's IR, but it's a different resistor this time, 0.255 times the 12 ohms. And so I get 3.064 volts. And then for the 25 ohm resistor, it's the same current, right? The same current goes through everything in this series circuit, but this resistor has a resistance of 25 ohms. And so I get 6.383 volts. Okay, so we found the voltage drop across each resistor. Let's show that Kirchhoff's loop rule applied in this circuit. So to do that, I need to show that the sum of the delta V's that were gains equal the sum of the voltage drops. So there's only one gain in this circuit because there was one battery, and the voltage increased by 12 volts as you went through the battery. And then there were 3 voltage drops. The voltage drops across all of those resistors. So let's see, do these equal or not? Does 12 really equal the sum of these things? And I get 11 0.997. That's pretty close. So I would say yes, we could calculate the percent difference. It's going to be small, right? It's going to be 12 minus that 11.997 divided by the 12. We'll make that a percent, and so that's 0.027% difference. Very small. So yes, Kirchhoff's loop rule applied in this particular circuit. It's actually going to apply in every circuit, but it's good to show that it does. Okay, let's look at one more. Here we have another circuit. Notice that in each of these, the resistance is given in, well, two of them are given in terms of kiloohms, so I need to interpret that prefix. So the equivalent resistance would be the sum of these three resistors. So it's 10,000, right? Because 10 kiloohms is 10,000 ohms, plus 25,000 ohms, plus 1,000. And so the total resistance here is 36,000 ohms. And so the battery current, we're using Ohm's law at the circuit level, is the delta V across the battery divided by that equivalent resistance. And so I've got 240 volts divided by the 36,000 ohms. Is 0.00667 amps, or 6.67 milliamps. Okay, so then to find the voltage drop across each resistor, I need to take or use Ohm's law at each resistance level, and so that's going to be the current going through the resistor times the resistance. The current for all of these is going to be the 0.00667 amps, and then this is by the 10,000 ohms, work in standard units, and so I get a voltage drop of 66.67 volts for that resistor. If I did the current times the 25 kiloohms, which is 25,000 ohms, the delta V across that resistor is 166.67 volts. And then finally, our last resistor is only 1,000 ohms, but it's the same current going through it. And so it has a much smaller voltage drop of just 6.67 volts. Okay, so to confirm Kirchhoff's loop rule, I want to show that the sum of the delta V's that were gains equals the sum of the delta V's that were drops. And that's because energy is conserved in the circuit. So there was only one battery in this particular circuit. There was one voltage gain of 240. And then I had three voltage drops. There was the 66.67, the 166.67, and the 6.67. And let's just see if those equal. And I get 240 equals 240. So yes, Kirchhoff's loop rule did apply to that circuit.